Assalamu alaikum. My name is Diffraction. I'm from Department of BS Biotechnology, and my roll number is 190082310005. Today, I'm here to present a presentation on XRG, and my fellow group member had already told you about the X-ray experiment conducted in 1895 by William. So now let's begin with the main topic: what is X-ray diffraction or XRD? X-ray diffraction or XRD is a technique for analyzing the atomic or molecular structure of a material. It is non-destructive and works most effectively with materials that are hollow or part crystalline. The technique is often known as X-ray powder diffraction because the material being analyzed typically is finally ground down to a uniform state. Diffraction is when light bends slightly as it passes through the edge of an object or encounters an obstacle or aperture. The degree to which it occurs depends on the relative size of wavelength compared to the dimensions of the obstacle or aperture it encounters. How does XRG work? X-rays are formed by electromagnetic radiation, including wavelength measurable in nanometers. A nanometer is equivalent to 1 billion of meter. When monochromatic X-ray scatters from a substance with structure on the scale is cause interference. This results in a pattern of lower and higher intensity due to the constructive and destructive interference according to the Bragg's law. With crystalline substance, the pattern created three-dimensional shavings of diffraction in response to X-ray wavelengths. Like the spacing of the planes in crystalline lattice, this process is known as constructive interference and is used as a technique for studying crystal structure and atomic spacing. All diffraction methods start with a emission of X-ray from cathode ray tube or rotating target, which is then focused at a sample. By collecting the diffracted X-ray, you can analyze the sample structure. This is possible because each mineral have a unique set of d-spacing, and d-spacings are the distance between the planes of atoms, which cause diffraction peaks. There are standard reference patterns of d-spacing, which act as a comparison when using XRD to identify the structure of a sample substance due to the earlier standard references of the peak of the spacing. The wave that actually reveals the atomic structure of crystals is based on Bragg's law. Here's a diagram of XRD that how that incident beam hits the crystalline material, and the diffracted beam changes the angle and hits the diffracting pattern recording plane. This shows that when the incident beam of X-ray is in the straight line, but after hitting the crystalline material, it changes its angle by 2 theta. Here's another example how that instrumentation of XRD are done. First of all, the X-ray tubes uses the voltage of 10,000 to 40,000 volts to produce X-rays. These X-ray hits the lead screen and passes through the lead screen. It hits the crystalline solid by which the structure of structure of crystalline substance can be seen. In the end, there is a photographic plate on which The spots of the X-ray that have been diffracted can be seen, and also the spots for the incident beam can also be seen on the photographic plate. It's also known as X diffraction pattern record. Let's come towards the Bragg's law. Bragg's Bragg's law will only occur. Bragg's law tells us that diffraction will only occur if the if the X-ray and the substance interact meets the condition of Bragg's law. The requirement for that is that the angle of incidence is equals to angle of scattering wavelength. The path length difference is equals to integer numbers of wavelength. This allows the condition of maximum intensity, which then enables a calculation about the details of the crystal structure concerned. In the end, it is shown that the Bragg's equation is equals to n lambda equals to 2d sine theta. Later, we will discuss how this formula had been derived. Here's an constructive interference of X-ray 2 that tells us that X-ray equation is used to solve many equations problems related to XRD and others. Bragg's equation helps to calculate the interspacing calculations between layers of atoms. As there are two layers of atoms, the upper and the lower, and the distance between the both layer is known as d, is denoted by d. The X-ray first of all passes on one atom have same angles as of incident ray and scattered ray. After the X-ray passes the angle, a triangle is formed as it is shown in this picture, that a triangle is formed with an angle of 90 degrees, and it has also an other angle which is known as theta, which is similar to this angle. The angle will form here and there. Both angles will be same, and the dotted line that is in this triangle is reference to the length d between the distance between the two planes of atoms or layers of the atom. This dotted line will be the hypotenuse. Then we sign the position by alphabetically, as known as A, B, and C. Means AB is equals to BC. Here's another picture of an triangle that has been drawn. That here the angle theta is introduced. D will be the hypotenuse, and the other angles, other sides of the triangle, has been denoted with the alphabets. So, for the more clarification, now will be see how this equation drives. As we know, n lambda means n will be the times for each time whenever the experiment take place, it will be lambda will be multiplied with that many times. It is equals to a b plus bc. So in the as we told earlier that ab is equals to the bc, as it is the ray of incidence is equal to the ray of scatter. So after deriving the equation, we will find out that n lambda is equal to 2ab. So ab sine theta is equals to ab over d. By multiplying this d with the sine theta, we'll find out that ab is equal to d sine theta. So we will put convert AB plus BC to d sine theta. After converting it, we will find out that n times lambda is equal to 2 sine d theta, which is Bragg's equation. This is how the Bragg's equation has been derived to solve the equations. This is the equations of the Bragg's law, and lambda is equal to 2d sine theta. D will be the distance between two layers. Each layers of the atoms have different angles and different distance. For so that's why it's important to find out the d and theta. So now we see that in this formula, n is the integer denoted the reflection order. Lambda is the X-ray wavelength. D is the lattice spacing distance between crystal planes, as we discussed earlier, and theta is the diffraction angles. What will XRD measures? X-ray diffraction can do the following things by measuring the average spacing between layers of rows of atom in a substance. It also determines the orientation of an individual grain or crystal and the space, size, shape, and internal stress of small crystalline area can also be measured by XRD. It also identifies the crystal structures of an unknown substance. Now comes towards the geometry. For the geometry in X-ray diffraction is such that sample rotates in that plane in the plane of collimated X-ray beam at an angle theta, while the X-ray detector is mounted on an arm to collect the diffracted X-rays and rotates at the angle of 2 theta. The instrument used to maintain the angle and the rotates the sample is termed as goniometer. For a typical powder pattern, data is collected at 2 theta from 5 degree to 70-degree angle that are present in the X-ray scan. Now, Bragg's law and diffraction. What is the relation? Diffraction occurs only when Bragg's law is satisfied. Conditions that are already been discussed previously. If all the conditions were, fulfilled, then we can apply the Bragg's law and Bragg's equation to find out the spacing and the angles and all about the atoms and molecules. Uh, next of Next, we will see that the planes in crystals are in two dimensions. It is being clarified that if after satisfying the Bragg's law, there must be change in theta and the distance between two layers of the atom. If the this theta decreases, means the distance between the two layers increases. They are inversely proportional. Now, what is the difference between XRD and XRF? The basic difference between X-ray diffraction and X-ray fluorescence is what each method are can determine by these two things that X-ray determines the mineralogy of a sample with identification, and XRF determines the chemistry of a sample elemental composition. Here's another basic of crystallography that the D is the distance of each layer uh, and the three-dimensional x, y, and z are denoted with the specific numbers that 001 is z, 010 is y, and 100 is x. This is how they can easily identify the planes of the lattice, that how the size of a grain or a crystal. The crystal consists of a periodic arrangement of a unit cell. This is the unit cell of a CSCL of its unit cell into a lattice. Means the subunit of a lattice is unit cell. The unit cell can contain a single atom or a atom in a fixed arrangement. Means that they are in a fixed arrangement. Crystals consist of planes of atoms that are spaced a distance d. Means that the crystals are distance and the distance is denoted by d apart, but can be resolved into many atomic planes, each with a different d spacing. Means each size of each planes and the dimension have different types of d spacing. So for that, A, B, and C are denoted with the length, and alpha, beta, and gamma are the angles between A, B, and C. And and lattice constants or parameters which can be determined by XRD. Now, what equipment do you need for XRD? The instruments required are X-ray cathode tube for the production of X-rays, sample holder, the powdered or any form of the samples which are going to be studied through XRD, and in the end the X-ray detector. As I shown you the picture of an X-ray, that X-ray producer that produces X-rays at the voltage of 10,000 to 40,000, and the NA photographic film detector that to detect the X-ray detector. The cathode tube generates X-ray through applying heat to a filament. This produces electrons which are then detected towards a target by applying a voltage. These bombard the target material designated inner shell electron within which they then produce X-rays. The X-rays are then detected into the sample, directed to on the sample. The source of X-ray detector in the instruments both rotates. When this geometric movement satisfies the conditions of the Bragg's law for the sample being analyzed, constructive interference occurs causing a peak in intensity. The detector records and processes this signal, converting it into count rate of or output of computer, typically represented intensity Vs theta versus theta. Now, how do you prepare a sample for XRD? There are three things need for the preparation of X-ray diffraction: the sample, substance, equipment or tools to grind it with, and a sample holder. First, take a few tenth of a gram of a sample substance, grind it to a firm powder. Typically, this should be done in a fluid to minimize any excess surface energy, which might otherwise randomize the sample. The optimized size of a powder is less than 10 micrometer. Next, place this ground powder onto a sample surface or within a holder. It is important to create a flatter upper upper sample surface with a random distribution of lattice orientation. Next, how do you collect and interpret XRD data? The X-ray diffractometer continuously records data during the process when both the sources and detector rotates. Peak intensity occurs when the d-spacing in the lattice plane of an mineral sample are approximately to the value of the diffracted diffractor X-rays. Results are presented in peaks positions and X-rays counts in a table. The Bragg's equation calculates the d-spacing of each peak. Once you know all the d-spacing in the sample, you can compare these to d-spacing of known material for identify purpose, typically commercially available databases. So the known d-spacing for reference are available from several sources. As we have discussed earlier that there are a lot of d-spacing references available to interpret the data for a new one. So what are the uses of X-ray diffraction? The main uses of X-ray diffraction is to identify unknown crystalline material. This uses the X-ray XRD is essential in geology, engineering, biology, mathematical science, environmental science, battery research, thin film coating, electronics, and, and a lot of others. Applying XRD for defining thin film sample, we need to measure the lattice mismatch between film and substrate to define stress and strain. Analyzing rocking curves to determine dislocation, density, and film quality. Measuring superlattice in epitaxial structures that are multi-layered. Analyzing glancing incidence, X-ray reflectivity measurements to determine the thickness, density, and roughness of film. Now comes towards the industrial uses of XRD. XRD is used in the pharmaceutical, forensic science, microelectronics, glass, geological, and many others. Now, what are the advantages and disadvantages of X-ray diffraction? The advantages are it is rapid and powerful technique for identifying unknown minerals and materials. It also requires preparation of a minimal sample for analysis. Interpreting the result data is relatively slight, straightforward. XRD measurements instruments are widely available. Now the limitation or disadvantages is that to best identify an unknown powder material, sample should be homogeneous. Typical XRD analysis requires access to standard reference data. Means there should be some kind of reference data related to that sample you are going to study or investigate. Preparing of sample often require grinding them down to a powder form. So you need to be very accurate or very careful while powder make converting the sample into powder. If the crystal sample is non-isometric, then the indexing of the pattern can be complex when determining unit cell. Thank you. That's all from my side. Allah Hafiz.